All right, let's think about the sun. Usually, we see it as this source of warmth, of light, our companion in the solar system.
Right. Pretty benign most of the time.
But it can also be this dynamic, sometimes really turbulent star, capable of unleashing just immense power.
Power that can really mess with our technology.
Exactly. And even pose a real threat to astronauts, to space explorers. And this isn't just theory. We're looking back today at 10 truly unforgettable days in August 1972.
Yeah, that's our focus for this deep dive. The extraordinary solar storms of August 72. We've looked at accounts detailing this really intense period of solar activity.
Trying to piece together what happened, the effects, why it mattered then, and importantly, why it still matters now.
Our goal, really, is for you to grasp the significance of these storms, why scientists are still studying them.
What were the potential dangers, and maybe the biggest question, why are they so relevant today in our super tech-heavy world? You might be surprised by the sheer speed and force of what happened.
It was pretty remarkable.
Okay, so let's dive in. Where did this all start, this intense period?
It really kicked off on August 2nd, 1972. That's when the sun entered this phase of, well, significant eruptions.
Like multiple events?
Yeah, a whole series of solar flares and also coronal mass ejections. CMEs, as they're often called.
Okay, CMEs. Remind us what those are exactly.
Think of them like huge burps from the sun's atmosphere, the corona. They blast out billions of tons of charged particles, plasma, and tangled magnetic fields into space.
Billions of tons. That's a scale that's almost impossible to really wrap your head around.
It truly is. And while these CMEs travel huge distances, one particular ejection from that period was exceptionally fast.
Faster than normal.
Oh, much faster.
Right.
Usually a CME takes maybe 2-3 days to get from the sun to Earth, across 93 million miles.
Right, that sounds about standard.
But this specific one launched on August 4th, 1972. It was anything but standard. It made that journey in just 14.6 hours.
14.6 hours. That's barely over half a day.
Exactly. Astonishingly quick.
Wow. I mean, sunlight takes 8 minutes. So this thing was moving at a serious fraction of light speed. That velocity is just staggering.
It really is, which immediately raises the question of danger.
Yeah, what kind of danger would that speed, that intensity pose to anyone outside Earth's protective magnetic field, like astronauts?
And that's where the near-miss part of this story comes in. Because back in 72, we still had the Apollo program running.
Right, missions to the moon.
Exactly. And the Apollo spacecraft, well, they had relatively thin aluminum shielding.
Okay.
It was fine for the usual radiation in space, but it offered pretty limited defense against the kind of intense, immediate blast of high-energy particles you get from a major solar proton storm like this one.
So when you say high-energy particles, are we talking about a serious radiation dose? Way more than just, like, a bad sunburn.
Oh, significantly more. This was a solar proton storm. A massive flood of high-energy particles, mainly protons, blasted out from the sun.
And the dope.
Estimates suggest that astronauts caught in this, outside the Earth's protection, could have absorbed doses between 1,000 and maybe 4,000 millisieverts.
How bad is that? Can you give us some context?
Well, just 5,000 millisieverts, whole body dose, is considered lethal for about half the people exposed within a month or two. So even at the lower end, say 1,000 millisieverts, you're looking at acute radiation sickness, severe immediate health problems.
That's a chilling thought. Really highlights the risks involved in space travel, doesn't it? And how much we rely on shielding.
Absolutely.
So how close did an actual Apollo mission come to being caught in this?
It was purely down to fortunate timing, really. Apollo 16 had already come back to Earth in April 72, months before the storm.
Okay.
And Apollo 17, which turned out to be the last moon mission, didn't launch until December that year.
So there was this window in August where things could have gone very, very wrong.
Exactly. If a crew had been traveling to the moon or working on the surface during those few days in August, the speed and intensity of that solar proton storm, it could easily have been catastrophic.
Wow, just incredible timing, but potential tragedy avoided just by the mission schedule.
Seems that way.
But this powerful solar event, it wasn't just a threat in space, right? It caused some weird effects down here on Earth, too.
Oh, definitely. There was one particularly strange incident in Haiphong Harbor, Vietnam.
What happened there?
Well, the U.S. Navy had laid sea mines there, magnetic mines, designed to trigger when a ship's magnetic field passed over them.
Okay.
And suddenly dozens of these mines just started detonating. For no apparent reason, there was, understandably, a lot of confusion.
Unexplained explosions usually cause confusion, yeah. So what was going on? How did the solar storm connect to naval mines?
It was the huge magnetic disturbance. When that CME slammed into Earth's magnetic field, it shook it violently.
Like ripples in a pond.
Sort of, but electromagnetic ripples. It caused these electrical currents to flow through the Earth's crust itself. They're called geomagnetically induced currents, or GICs.
BICs, okay.
And in Haiphong Harbor, these currents flowing through the seabed were actually strong enough to trigger the magnetic sensors in those naval mines.
Wow, so the sun basically set off the mines.
Indirectly, yes.
Sure.
Through disrupting the Earth's magnetic field so significantly, it's a really striking example of how solar activity can affect our technology in unexpected ways.
That's a connection you definitely wouldn't make immediately. Solar storms triggering mines. Wild. What other effects happened on Earth?
Well, radio communications took a big hit, especially high-frequency bands, HF radio.
Why those specifically?
Because HF radio relies on bouncing signals off the ionosphere, which is a layer in the upper atmosphere, and the ionosphere is very sensitive to solar storms.
Ah.
That massive influx of charged particles basically scrambled the ionosphere, changing its properties dramatically. So signals got weak, faded out, sometimes there were complete blackouts. Even some early satellite comms had issues, though the records aren't as detailed as for HF.
Right. I can imagine the frustration for anyone relying on that. Pilots, military, shipping.
Absolutely. And
Yeah.
then there were the Auroras.
Ah, yes, the northern and southern lights. I read they were seen way further south than usual.
That's right. Auroras are usually confined to the polar regions, where Earth's magnetic field lines funnel particles into the atmosphere.
Yeah.
But this storm was so intense, it pushed those auroral displays much further towards the equator. We have documented sightings as far south as Texas, and even in Spain.
Texas and Spain, that's incredible. What did they look like?
Reports often mentioned eerie greens and purples. Quite unusual colors for those latitudes, adding to the strangeness of the sight for people who'd likely never seen an aurora before.
Must have been quite something to witness. Beautiful, but also a bit unsettling, knowing what was causing it.
Definitely an otherworldly sight, driven by this immense solar power.
Now, one thing I found interesting is that, despite all this disruption, the power grids back then didn't seem to suffer widespread failures like we worry about today. Why was that?
That's a really important point. The geomagnetic disturbances were absolutely huge, no doubt about it.
But the grids held up.
Largely, yes. And the main reason was the nature of the electrical grid in the 1970s. It was, well, simpler, less complex, less interconnected than the vast, sprawling grids we rely on now.
So those geomagnetically induced currents, the GICs we talked about.
Exactly. While they were definitely flowing, they just didn't have the same extensive pathways to travel along, or the same concentration of highly sensitive, critical equipment to potentially overload compared to what we have today.
Makes sense. Less complex, fewer weak points, maybe.
In a way, yes. But the key takeaway wasn't that the grids were immune. It was more like a grim preview, a warning.
A warning of what could happen to our modern grids if a storm like that hit today.
Precisely. The August 1972 event served as a stark, even if unintentional, wake-up call about the potential vulnerability of our much more sophisticated, interconnected power infrastructure.
So it was disruptive, yes, but also kind of a crucial lesson. It wasn't just some interesting space weather event. It had real-world consequences and highlighted future risks.
Absolutely. And that leads into the lessons learned.
Okay, so what were the big takeaways from this whole period?
Well, for starters, the August 72 storms really became a foundational case study for space weather science, which is still a pretty young field then.
It put space weather on the map, so to speak.
You could say that. It shifted the understanding of solar storms from being, maybe a bit abstract to being a very tangible hazard with potentially serious consequences. NASA, the military, space agencies worldwide, they all took notice.
Recognizing the threat, especially for space missions, which were getting more ambitious.
Right. And that new awareness directly led to changes in how we design spacecraft and how we operate them.
What kind of change?
Well, crucial safety features became standard. Things like dedicated radiation shelters inside spacecraft, kind of like a storm cellar for astronauts during a solar particle event.
Okay, that makes sense.
Also, more robust electronics, hardened electronics, designed to resist radiation damage. And, critically, much better real-time solar monitoring.
Watching the sun constantly.
Yet dedicated satellites and ground telescopes observing the sun 24/7, looking for signs of potentially hazardous activity flares, CMEs starting to lift off. This gives us warning time.
Time for astronauts to get into those shelters, or for ground control to maybe power down sensitive equipment.
Exactly. That warning time is vital. The International Space Station relies heavily on this, and any future missions to the Moon or Mars absolutely depend on the knowledge we gain from study events like 1972.
So we're much better at seeing these things coming now. But can we actually stop them? Is there like a giant space umbrella we can deploy?
Wouldn't that be nice? But no, unfortunately not. Our prediction and monitoring have improved hugely, which is critical for preparation.
But we can't prevent the storm itself.
No. Once a massive CME is launched and heading our way, there's currently no technology to deflect it or weaken it. All our efforts focus on better understanding the sun, improving forecasts, and developing protective strategies for our technology and astronauts.
That's a sobering reality check, isn't it? Despite all our tech, we're still fundamentally subject to these massive natural forces, especially from our own star.
It really puts things in perspective.
So thinking about those 10 days back in August 72, what's the big picture? The broader significance of it all?
I think the August 1972 storms are this powerful reminder of the sun's dual nature. It gives us life, obviously.
Yeah, the ultimate life source.
But it also holds the potential to seriously disrupt, maybe even endanger, our technological civilization, which is increasingly dependent on systems vulnerable to space weather.
Right.
Many scientists see those events as a genuine planetary warning shot. They showed us the raw speed and power of solar storms in a way nothing really had before.
It wasn't just an abstract risk anymore. It was a demonstrated capability of the sun.
Exactly. It wasn't just some interesting blip for scientists. It fundamentally shifted our view of our place in the solar system and our relationship with the sun.
So it really changed things.
It ignited a global awareness, you could say, of space weather as a serious issue. It reshaped how we prepare for these hazards coming from, 93 million miles away. And that shift continues to influence space exploration, satellite design, even how we manage power grids today.
Okay, so wrapping this up then. Those solar storms back in August 1972, they were way more than just some fancy light shows in unusual places.
And much more.
They were this extraordinary, potentially catastrophic event that really laid bare the sun's immense power. And also the vulnerabilities in our technology and our space ambitions when faced with that kind of energy.
That sums it up well as a profound wake-up call.
And it leaves us, and you listening, with a pretty important thought to consider, doesn't it?
I think so. In our world today, which is more connected, more reliant on sensitive technology than ever before, how ready are we really for the next big one, the next planetary warning shot?
What vulnerabilities might we not even be fully aware of yet? And how do we keep improving our resilience, living alongside this magnificent but sometimes volatile star that rules our solar system? Something to think about.